Welcome to part 3 of the lecture on automatic parallelization. So far we have learnt about data dependence relations. There are 3 types of relations: flow, anti and output dependence. Then we learnt about the data dependence direction vector, which is one of the most important concepts. So basically, if there are nested loops, we look at and let us say two statements nested within the loop. So we look at instances of these statements SV and SW. That means for some iteration values I1 to ID and J1 to JD, we look at the statements which are executing with those iteration values at that instant, and those are called the instances. So if there is a dependence between these two statements, that means the value which is computed in SV is actually used in SW, and the relationship between these iteration counter values I1, J1, I2, J2 etc., is captured by the theta function. So if the increments are positive, then theta would be a very simple function, theta ik equal to ik. And if the loop increment is negative, then we just say theta ik equal to minus ik, and that is how the relationship would be. There are 3 types of direction vectors possible: less than, greater than and equal to. Less than means that the dependency is from the iteration I to I plus k. Greater than means that the dependency is from iteration I to I minus k. That means this is not possible in single loops. Equal to means that the dependency is in the same iteration, computed in iteration I and used in iteration I itself. So here is a very simple example to help you recapitulate what we have done. So in this loop, in this example there are 2 loops I and j. There are 2 statements S1 and S2. So if we to look at the dependence between these 2 statements, observe Aij on the left hand side of S1 and on the right hand side of S2. These 2 have identical subscripts, and when we unroll the loop, we know that A11 is computed in I equal to 1 and j equal to 1, and it is also used in the same iteration I equal to 1 and j equal to 1. So between these 2 there is a dependence S1 delta equal to S2, because we have the same I and j values for both these instances of statements S1 and S2. Similarly, between these 2 B12 and B12, we have a dependence from S2 to S1 with the direction vector equal to and less than. So that is because it is S2 computes B12 with I equal to 1 and j equal to 1, and S1 consumes the same value B12 with I equal to 1 and j equal to 2. So the relationship between I is the equal to, and between j's it is 1 less than 2. And thirdly, S2 delta equal to less than S2 is a loop here in the dependence diagram. So that arises because of this B13 which is computed in S2 and used in S2 again, but with a different j value. I value is the same. And here is an example of S1 delta less than greater than S2. So this is possible because I value increases from 1 to 2, but j value decreases from 2 to 1. This is legal because we are really looking at a different set of iterations of j for a different value of I. So there is no illegality here. Similar example on this in this part as well. And finally, here is the example which shows that there is a dependence from S1 to S2, S1 to S2 with delta equal to and less than. So that is shown here, equal to and less than. So computed here and used here, x1 to k, x1 to L. So S1 and S2. So these 2 actually show that dependence. And similarly, this is from S2 to S1, A21L and A21L. So this is again delta less than equal to. So what is computed here is used here. So these are the examples that we have already looked at. Then we saw the execution order dependence and direction vector. So basically we are looking at the flow of the program, and if we say that if SV can be executed before SW, then we have SV theta SW, and this execution order dependence is weaker than the data dependence itself. So, that example is here, we will not repeat the example again, and there is a direction vector attached to this execution order dependence in exactly the same way as we attached one to the data dependence itself. Now, not all direction vectors for execution order dependences are possible. So, we can consider actually the legal execution order direction vectors by looking at the syntax itself. So, here is a very simple example for this particular loop nest, you know, S1 theta equal to less than equal to S2 etc., are all possible, but S2 theta equal to S1 is not possible for the simple reason, you know, S2 is we cannot reorder the statements at all, you know, this S1 and S2 remain the same. So, we really cannot reorder statements. So, in the same iteration of I and j, we cannot execute S2 first and then S1. S1 theta equal to greater than S2 is obviously not possible, because greater than is a relationship which is valid only when the first one is less than. So, then we looked at the data dependence equation. So, there are two statements SV and W which have the array references x of f I1 to id and x of g I1 to id. So, there is a loop nest of 1 to d, okay. And here we have you know, f I bar is a naught plus k equal to 1 to d sigma a k I k. So, this is just show that the constraint on the form of the subscript is basically that it should be a linear function of the loop indices. Similarly, the second one is also a linear function of the loop indices. So, now we try to find solutions for I bar and j bar for the equation f I, you know, this f I bar equal to g I bar. So, then the dependence equation is satisfied as f I bar equal to f j bar. So, those values of I bar, little I bar and little j bar are the ones we try to find. But when we satisfy that equation, the direction vector relationship must also be satisfied. So, there will be say I1 less than I2 etc., these are the relationships which will be satisfied. So, we also try to normalize the index. So, that is dealt with here, you know, so that we have an increment of 1, loop bound, lower bound as 1 etc., The relationship between the loop index variables with the normalized and unnormalized versions is here. This is a fairly straightforward Lk plus Ik and Nk is equal to Ik. So, that is the relationship. With that we modify the equations here, but then, you know, from now on we are just going to assume we will use the now that always the loops are normalized with loop lower bound as 1 and the increment as 1. The GCD test we briefly looked at. So, we have a dependence equation a1 x1 plus a2 x2 etc., an xn, and then the right hand side the other statement would have b1 y1 b2 y2 etc., bn y1. So, when you know, and the constant values are b naught and a naught. So, if we solve this equation, when this is equal to b naught minus a naught, then we have found a solution to the dependence equation. So, this has been shown to have a solution if and only if GCD of a1 to ad and b1 to bd divides b naught minus a naught. So, we will see examples of this now. The GCD test is very quick, but not very effective in practice. We will see that very soon, and it indicates dependence whenever the dependence equation has a solution anywhere, but not necessarily within the region imposed by the loop bound. This is the major problem. So, and when we have a direction vector also available and we want to test for a particular direction, that is possible. Only equal to direction can be tested separately. So, let us say the function gamma psi comma omega is k such that psi k is equal to omega, where omega is one of the direction vectors. In other words, we are trying to pick the component of the direction vector which is equal to omega. That is what this gamma function does. So, when we are testing for a specific direction vector psi, sum of whose directions are equal to, then the above condition what we saw, the GCD condition can be slightly tightened. So, what we really do is pick those components of rather those coefficients which correspond to the equal to value of the direction vector and make that as a k minus b k into n k. The others remain as they are. So, only thing is instead of a k, b k etcetera, now we use a k n k, b k n k etcetera for the others, and the condition would be modified slightly as b, the divides b naught minus a naught plus the sigma of k equal to 1 to d b k minus a k l k. So, whereas here we just had GCD of a1 to a d, b1 to b d divides b naught minus a naught. Here we have a k minus b k into n k, similarly a k n k, b k n k for the rest of them, and on the right hand side we have b naught a naught plus the sum of the b k minus a k into l k. So, this even this test is not very effective, and the problem is it requires L k, it requires the direction vector and so on and so forth, but we cannot use such a test so effectively with other combinations of direction vectors, for example, less than etcetera etcetera, which can be used only with equal to. So, this is not very useful to us later on. So, let us look at some examples. So, here is a loop a I equal to 1 to 10 do. So, S1 is a I equal to something and S2 is dot dot equal to a I. Now, we can see by if you unroll the loop, we see that A1 equal to A1, A2 equal to A2 etcetera. So, the dependence is within the iteration. Okay. So, it does not go beyond the iteration. So, we have S1 delta equal to S2, that is the dependence in this particular loop. So, let us see what the dependence equation is. So, on the left hand side we have I, so that becomes I1. On the right hand side expression we have I again, so that becomes I2. So, instead of writing this equal to this, we simply wrote I1 minus I2 equal to 0. So, that is our dependence equation. Here A naught is 0, A1 is 1. So, this is A1, B naught is 0 and B1 is 1. So, that is this. Now, the GCD test becomes GCD of A1 B1 divides B naught minus A naught. So, GCD of 1 comma 1 divides that B naught minus A naught is 0. So, 1 divides 0, which is true. So, this should have been 0, hence the dependence exists. That is what the dependence, the GCD test really tells us. However, the direction vector, the direction of dependence S1 to S2 or vice versa, and the type of dependence flow, anti or output, these are not indicated by the GCD test. Okay. So, example number 2. So, we have I equal to 1 to 9, AI on in S1 equal to something, and in S2 we have something equal to A of 10 minus I. This is special. So, if you unroll the loop, you see that you will have A1 equal to A9, A2 equal to and here is A8, A3 equal to A7, A4 equal to A6 and A5 equal to A5. Then the loop kind of runs in the other direction, A6 equal to A4, A7 equal to A3 etcetera etcetera. So, in the first half of the loop from say 1 to 4, we would have S1 delta there AI would be assigning some this statement S1 would be assigning something to AI. So, A1, A2, A3, A4 etcetera are being assigned, whereas the values of A9 here on this side we would have A9, A8, A7, A6 etcetera being read. So, in the first half of the loop we will have S1 delta whatever is in the middle of the loop, not in the first half of the loop. In the middle of the loop we will have A5 equal to A5. So, that dependence will give us S1 delta equal to S2. Okay. So, that is where one of these equal to dependencies comes, and then we have assigned and then read, right. So, these two reverse when the loop runs from 6 to 9. So, we get S1 delta less than S2 and S2 delta less than S1. Okay. So, together in the two halves of the loop we are going to assign and read the same locations. So, that is how S1 delta less than S2 and S2 delta bar less than S1 come into picture. So, this becomes these two are actually going to cause these dependencies. So, let us see what happens in the dependence equation. I1 plus I2 equal to 10 is the dependence equation. Why? This would be I1, this would be I2 and this is 10. So, I1 equal to 10 minus I. So, that would not be nothing but I1 plus I2 equal to 10, that is the standard form of the equation. A naught equal to 0. So, A1 equal to 1, B naught equal to 10 and B1 equal to minus 1. Okay. So, that is this is B1, this is A1. So, this is B naught. Okay. So, A1 equal to 1, B1 equal to minus 1. Now, the GCD becomes GCD of 1 comma minus 1, this and this, okay, divides 10. So, that means 1 divides 10, which is correct. Okay. So, the dependence exists. However, again we can't determine the direction vector, direction of dependence, type of dependence, etc., by this GCD test. So, we are going to look at the same examples with Banerjee's test, which is slightly more powerful than this a little later. So, now again another so far the two examples we saw told us that there is dependence. Okay. Now, let us look at an example where there is no dependence. This is A of 2 star I and this is A of 4 star I plus 3. So, if you expand the loop, you see that this will be A2, A4, A6, etc., etc. And here we would have 4 plus 3, 7, I equal to 1, this becomes 7, then I equal to 2 becomes 8 plus 3, 11 and so on and so forth. So, 11 plus 4, 15 and so on. So, this and this is even and this is odd, they never intersect. So, that means there will be no dependence between S1 and S2. What does our dependence test tell us? So, the equation is that here this side will be 2 I1 and this side it will be 4 I2 plus 3. So, we have 2 I1 minus 4 I2 equal to 3. So, this is A1, this is B1, this is B naught minus A naught. So, again we have a GCD of 2 comma 4, 2 comma 4 divides 3, which is false. So, that means there is no dependence. So, in the previous two examples, this and this, when the test said there is a dependence, it is a conservative estimate. In other words, there could be dependence, possibly there is no dependence as well. But if the GCD tests that there is no dependence, there is no need to test further. So, that is how the GCD test is. So, now the next example, is here. So, here we have AI in S1 and in S2 we have AI plus 10. So, actually speaking there is no dependence between the two, because the loop is running only from 1 to 10. Okay. So, this will be A1, this will be A11, this will be A2 and A12, etc., etc., and then the loop stops at A10. Okay. So, this becomes A20. If the loop had run a little further, okay, so say 15 or something like that, this would have become A11, A12, etc., and we would have possibly had some dependence. Okay. So, this would have in the I equal to 1, this would become A11. So, we would have computed into A11 in iteration number 11, but since the loop runs till only 10, there is no dependence between S1 and S2. The dependence equation is I1 equal to I2 plus 10. So, that is I1 minus I2 equal to 10. This is A1, this is B1 and this is B naught minus A naught. So, that means we get GCD of A1 B1 divides B naught minus A naught, that would really become GCD of 1 comma 1 divides 10, which is true. So, the GCD test really tells us that there is dependence, but there is really no dependence. So, this is the conservative nature of the GCD test. Why did this happen? The problem is from I equal to 11 onwards the dependence really begins, but I equal to 11 is outside the bounds of this particular loop, but GCD test does not worry about the loop bound. Therefore, it is unable to decide that there is no dependence between S1 and S2. So, the next form of test, which is more powerful, called the Banerjee's test, will take this into consideration. So, what is exactly Banerjee's test? So, let us understand this carefully. To begin with, we must look at some some definitions before we understand the notation and the Banerjee's test. We define what is known as the positive part and negative part of a real number. r plus is 0 if r is less than 0. So, this is a positive, and if it is a positive number r greater than or equal to 0, then it is just the number itself. So, this is the positive part. In the negative part r minus, it is r if r is negative and it is 0 if r is positive. So, this is negative part of the number. So, what we really do is we try to find the existence of a solution to the dependence equation under the constraints of a direction vector and also the loop limits. So, basically let us look at the dependence equation again. So, k equal to 1 to d a k I k minus b k I k is equal to b naught minus a naught. So, this is our dependence equation. So, now we want to find a lower and upper bound for k. So, k equal to 1 to d, the values of k are nothing but the they correspond to the loop indices, it is a de-nested loop, that is what we are looking at. So, for each k we want to find a lower bound and upper bound such that LBK psi k. So, again psi k is the direction vector component of psi is less than or equal to a k I k minus b k I k less than or equal to u b k psi k. So, here is a lower bound and here is an upper bound. Let us sum these constraints one by one. So, we would have LB1, LB2 etcetera here, UB1, UB2 etcetera here, A1, I1, B1, I1 etcetera here. So, you sum up all this, you get k equal to 1 to d of LBK, k equal to 1 to d of UBK, and in between we have k equal to 1 to d AKIK minus BKIK. So, this middle thing is nothing but B naught minus A naught. Therefore, we get k equal to 1 to d of LBK psi k less than or equal to B naught minus A naught less than or equal to k equal to 1 to d of UBK psi k. So, there are what Banerjee has really done is to provide the equations to compute LBK psi k for each type of direction vector in terms of the coefficients of the dependence equation. So, those are here. So, now what is the advantage of this particular set of constraints? That is here. So, if the constraints are violated, in other words, see it should be this LBK psi k sum should be less than or equal to B naught A naught, B naught minus A naught. Suppose this is not so, or on this side B naught minus A naught must be less than or equal to the sum of UBK psi k. Suppose this is not so, either one of them is violated, then if either this first side is violated or the second side is violated, then the functions cannot intersect under the constraints of the direction vector. So, then that means independence in that particular direction vector part. So, we are assuming that the loop increment is greater than 0, but otherwise we can use the inverse of the direction vector, which we will tell you later, and then switch LK and UK and use the absolute value of NK. So, no generality is lost if we use that the increment is greater than 0. So, if psi k is less than, so that is one of the direction vector components, psi k equal to is the second direction vector component, greater than is the third one, and star is the last. So, for each of these combinations, Banerjee has provided equations to compute LBK. Okay. So, this is LBK less than, LBK, UBK less than, LBK equal to, UBK equal to etcetera etcetera. How do we read this right hand side? So, this AK minus is nothing but the negative part of the number AK, and AK minus minus BK, the whole thing again minus means that if this number is positive, this minus really says it will be a 0. If this number is negative, then we use the number as it is. Then we have UK minus LK minus NK. So, UK and LK are the upper and lower bounds of the loop level at level k, and then we have the coefficients AK minus BK into LK, that again the kth level coefficients minus BK NK. So, that is how we read this, and this side is AK plus. So, that means it is the positive part of the real number, AK plus minus BK whole thing plus. So, if this number is positive, we take it as it is, but if the number is negative, we make it a 0. The rest of it remains the same. Similarly, for psi k equal to, we have 2 equations, and then psi k equal to greater than, we have 2 more equations, and psi k equal to star, which means it is really any direction, has 2 more equations. So, the star in the, if it is a singly nested loop or even doubly nested loop, without the use of a hierarchical dependence test, this star is useless. We are going to see the hierarchical test a little later. So, star is usually ignored if it is not a specific direction, okay, and greater than is ignored since it is not a feasible direction vector in single loops. So, we are really going to have only the less than and equal to direction vector components. Star is very useful in the hierarchical dependence test. So, we are going to see that a little later. So, that, but even then direction vector, the direction of dependence either is whether it is S1 to S2 or vice versa, and the type of dependence flow, anti or output are not indicated by the Banerjee's test. So, we need to use the execution order direction vector for this purpose, and we will see how to do this a little later. So, let us look at some examples of using Banerjee's test. So, we are going to run through the same examples that we did as before. So, we have AI here and AI here. We know that this dependence is S1 delta equal to S2. It is the same example that we saw during the GCD test. Dependence equation is I1 minus I2 equal to 0. GCD test returns true and says there is a dependence. But what does Banerjee's test say? Obviously, it can either say yes or it can say no. So, just for this example, let us see what A minus etc. are. So, we know that A naught is 0 here and B naught is also 0, and A1 is 1 and A2 is 1. So, A1 minus is 0 because A1 is plus 1, A1 plus is 1 because that is the positive part, B1 minus is 0 because B1 is also a plus positive quantity and B1 plus is 1. So, if we substitute these values in the equations for LB star, LB less than, LB equal to and LB greater than, we get these values. LB star becomes minus 9, LB less than also is minus 9, LB equal to is 0 and LB greater than is 1. B naught minus A naught is 0, that we know here, B naught this side is 0, and if we substitute the values and calculate UB star, UB less than, equal to and greater than, we get UB star as 9, UB less than is minus 1, UB equal to is 0 and UB greater than is 9. So, that means now you are ready to really check the constraint. So, LB star equal to minus 9, this is less than or equal to 0, no problem, it is definitely satisfied, and 0 less than or equal to 9, that is also satisfied. What I would like to point out here is, when we check for star dependence, if there is dependence in any of the other with any of the other direction vectors, this star dependence constraint will always hold. Okay. So, if that is showing a non dependence, then there can be no other dependence which is possible, because this star really stands for any type of dependence. Then LB less than is minus 9, this is less than or equal to 0. So, it is this part minus 9 less than or equal to 0 is indeed satisfied, but 0 less than or equal to minus 1 is definitely not satisfied. So, the constraint is violated. That means, there can be no direction vector component with less than. So, this is not satisfied. With equal to, we have LB equal to 0, less than or equal to 0, less than or equal to another 0. So, this is satisfied. So, that means dependence exists with this direction vector. I did not write that comment with star, because star really stands for any direction vector. So, equal to direction, there is a direction vector, there is a dependence, and that we know is true. The last one greater than, this is shown only for completion. With a single loop there can be no direction vector with greater than direction. This is 1 less than or equal to 0 is 0 greater than or equal to 1 is obviously not satisfied, and 0 less than or equal to 9 is satisfied, but one side is enough to kill the constraint. So, this is not satisfied. So, the only one which is satisfied and is meaningful is the LB equal to. So, we know that there is a dependence with direction vector equal to, but we do not know whether the dependence is from S1 to S2 or from S2 to S1. We do not know whether it is a flow dependence, anti dependence or output dependence. Let us look at the next equation. This was very interesting because it had many direction vectors equal to, less than and another less than, and there is anti dependence as well. So, first one is from S1 to S2, second one is from S2 to S1. The dependence equation is again I1 plus I2 equal to 10, no problem with this, and then the GCD test said there is dependence. So, let us see what the Banerjee's test says. I did not write down LB and UB for star and greater than, because we know it is not useful. Star will always be true if there is a dependence, and greater than will always be false for single loops. So, LB less than is 3, B naught minus A naught is 10, and UB less than is 17. So, 3 less than or equal to 10 less than or equal to 17 is satisfied. So, there is definitely a direction dependence with the direction vector less than. So, that is true. S1 to S2 also there is less than direction vector, S2 to S1 also there is less than direction vector. So, this is correct, but we do not know which one is which, okay, or both are true, but we do not know whether both are true or one of them is true. For equal to, it is 2, less than or equal to 10, less than or equal to 18, again this is satisfied. So, the equal to direction vector also exists, that is also correct, because S1 with delta equal to S2 holds. So, the dependence actually that pointed out by the GCD test is indeed correct here. Third one, GCD test there is no dependence. So, Banerjee's test obviously should say there is no dependence. So, again the dependence equation is 2I1 minus 4I2 equal to 3. The GCD test there is no dependence, said there is no dependence, and the Banerjee's test also says LB less than is minus 26, V naught minus A naught is 3, and UB less than is 2. So, 2 greater than or equal to 3 is obviously not possible. So, this is not satisfied. There can be no dependence with direction vector less than. With equal to, this is minus 20, less than or equal to 3, less than or equal to minus 2 is obviously not satisfied. Again there can be no dependence with equal to as well. Star and greater than are not useful, as I told you earlier. Now, this really shows the power of the Banerjee's test. So, AI equal to AI plus 10. So, there is really no dependence between S1 and S2. The dependence equation is I1 minus I2 equal to 10. The GCD test said GCD of 1 comma 1 divides 10. So, there is dependence. So, let us see whether GCD Banerjee's test also says there is dependence, or it says there is no dependence. So, we compute LB less than, that gives us minus 9, B naught minus A naught is 10. So, minus 9 less than or equal to 10 less than or equal to minus 1, obviously not satisfied. So, there can be no dependence with the less than direction vector. With equal to, it is 0, less than or equal to 10, less than or equal to 0 again. So, obviously not satisfied, hence there can be no dependence with equal to and less than either. Star and greater than are not useful as before. So, that means Banerjee's test says there is no dependence possible. The GCD test said there is dependence. The obviously GCD test is less powerful than Banerjee's test, and the dependence which really does not exist because of the loop bound being 1 to 10 is indicated here. So, if the loop bound increases to say 100 or something like that, this equation will indeed show that there is dependence. Okay. So, that is from the Banerjee's test as well. So far we saw how to apply the GCD test and the Banerjee's test independently. We really did not see how to apply it when there is a nest of loops, more than one loop nest, okay. And then there may be many combinations, and then there are also subscripts possible for arrays. Many the array we have seen so far had just one subscript, one dimensional array, but there could be multi-dimensional arrays, there could be multiple loops. So, the number of possibilities really becomes very large. So, how do we do that? We really do not know. The hierarchical data dependence test gives you a way of determining the dependence when there are multiple subscripts in an array expression. So, for example, SV and SW are nested in a loop nest of depth d. The two arrays are obviously X. We did not write the complete statement, we just wrote the references. First subscript is F1 of I1 to ID, second subscript is F2 of I bar stands for I1 to ID, third subscript is F3, similarly the sth subscript is Fs. So, there are S subscripts, okay, S dimensional array. Similarly, SW has G1, G2, G3 etc. Gs. Now, how do we go about testing whether there is dependence between these two statements or not? Obviously, if we test the subscripts separately, that is F1 and G1, F2 and G2, F3 and G3, Fs and Gs, and check whether there is intersection or not, we get some answers. How do we combine these answers and check whether there is dependence at the complete array level? That is what we want to know. So, this the method is simple. We test for both SV delta star SW and SW delta star SV simultaneously. That is the first statement. How to do that? We will see. So, the particular type of dependence delta, delta bar, delta naught depends on the position of the references and the direction of dependence. Okay. So, how do we use this? We will see a little later. We first test to see if the array regions accessed by the two references intersect. So, obviously, the subscript functions are equal simultaneously. So, that means F1 of I1 to ID must be equal to G1 of I1 to ID. At the same time, F2 of I1 to ID must be equal to G1 of J1 to JD for the same values. All of them must be equal, F1 equal G1, F2 G2, Fs equal to Gs for the same values of G1 and GD. If we knew the values of I1 to ID and J1 to JD, all this was very easy to find out, but we do not. We only have tests which check whether there is a dependence or no dependence between two reference equations. So, we start off with a direction vector star comma star comma star and test for the dependence using either the GCD test or the Banerjee's test. Okay. So, if independence can be proven at this level, then the regions accessed by the two references are obviously disjoint. So, the GCD test says independence with this direction vector. So, that is the one we already studied. What it really tests is if you say GCD of A1 comma B1 comma etc. divides P naught minus A naught, that test is for star comma star. And if it is for Banerjee's test, we know how to compute LB star, UB star and so on and so forth for each one of the direction for the loop bounds, okay, loop variables. So, then the regions accessed by the two references are disjoint. If all of them, if this direction vector test gives you independence, everything is the problem is solved. Suppose the test says there is dependence, then one star in the direction vector is expanded to less than, equal to and greater than, and the testing is continued with these three refined direction vectors. So, this is the hierarchical expansion that is done one at a time. Start with star comma star, test at this level using say either the GCD test or the Banerjee's test. If we find that there is dependence, then we expand the left star, less than comma star is tested. So, for this we cannot apply GCD test, we will have to apply only Banerjee's test. So, equal to comma star and greater than comma star. So, if we find that there is no dependence at any one of these stages, for example, this is not a feasible direction vector, first component cannot be greater than in a direction vector, right. Only the second onwards it can be greater than, provided the first component is a less than. So, there is no need to really expand this tree and test for more dependence here. We can simply say this is not possible, prune this tree at this point. But out of these two, if one of them says there is no dependence, the test says no dependence, that tree need not be processed further. But suppose both of them say dependence is present, then we need to actually expand further. This becomes less than equal to, less than greater than. This becomes first component is equal, second is less than, equal to or greater than. So, this is again not possible, we know that, okay, but this is possible, all these 5 are possible. So, we need to check for dependences with these direction vectors one at a time using the Banerjee's test, okay, and then see which one returns true and which one returns false. So, now, whatever is returned as true remains and whatever is returned as false just goes away. So, we collect only those dependencies which are returned as true. So, we did this for each subscript, right. Now, we also need to understand how to combine the direction vectors of various subscripts and get one direction vector product. So, that requires the definition of what is known as a product of direction vectors, and if we know that there is no dependence from S1 to S2 for some reason, somehow we know that, then we need to check whether there is dependence from S2 to S1. To do that, we need to compute, suppose we have already computed the direction vector from S1 to S2 and we want to compute now the direction vector from S2 to S1. That requires complement operation on the direction vector. So, the complement operation, we do not have to compute the new direction vector all the way starting with the Banerjee's test. So, what is the complement of a direction vector? Psi is psi 1 to psi d and psi inverse is psi 1 inverse etcetera psi d inverse. How do we compute it? If psi k is less than, psi k inverse is greater than. So, if there is a dependence from S1 to S2 with a less than, then in the complement it will become greater than. If it is equal to, it remains as equal to, greater than becomes less than or equal to becomes greater than or equal to, greater than or equal to becomes less than or equal to, not equal to remains not equal to and star remains star. So, this is how we compute the inverse. So, this will become clear a little later. What about the product of two direction vectors? So, if we have a 2 dimensional array and we compute the direction vectors for each of the subscripts separately, how do we compute the direction vector of the entire reference? We need to take a product of these two dv's. So, let us say psi 1 is psi 1 1 to psi 1 d, psi 2 is psi 2 1 to psi 2 d. So, psi is psi 1 to psi d, which is defined as psi 1 cross psi 2. So, you just take the cross product of the individuals. How to do that? Is in the next slide. So, psi 1 1 cross psi 2 1, psi 2 1 2 cross psi 2 2 etcetera etcetera, psi d equal to psi 1 d cross psi 2 d, and the cross operator is defined later. So, in the next in this slide, whenever we have a dot, that means it is a null direction element, it is not possible, that is why it is null, and whenever we reach a null, that means there is no dependence. So, one of the subscripts has a less than direction vector, the other subscript returns a less than direction vector, then the product is also less than. So, imagine if you have a 2-dimensional array, one of the dependence in one of the dimensions is less than, the other is also less than, then it makes sense to have the entire dependence as direction as less than. But suppose one of the direction vector says it is less than, that is you compute in iteration I1 and use in iteration I1 plus k. The other subscript says equal to, that means I compute in I1 and use in I1. So, obviously, there is a difference of opinion between these two direction vectors, and when we take a product it would yield a null, that means no dependence is possible. Similarly, less than and greater than would give a null, less than and less than or equal to will give a less than, okay. Less than and greater than or equal to will give a null, etc., etc., etc. With the not equal to and star you just get less than. So, that is how the direction vectors are really computed. With equal to we have just one, with with another subscript also being equal to we get equal to, otherwise less than or equal to we get equal to, greater than or equal to we get equal to, not equal to will give a dot and star gives an equal to. So, this is how we compute the product of direction vector. Now, what? Compute the, so what is the data dependence direction framework? The product of direction vectors corresponding to the various subscripts is obtained, and then we get one direction vector. So, that is the next step. We have the direction vectors for the various subscripts. So, now we have a single direction vector. So, we defined the direction vector for product direction vector for Si1 cross Si2, but it is easy to see that we can do this and then another cross and third cross, etc., etc., and get Psi. Suppose this combination produces any dot entries, then that means in this direction vector we have less than, comma, greater than, comma, equal to, comma, dot. Then there is no simultaneous intersection between these direction vectors, one of them is a dot. So, it is a not possible direction vector and there can be no dependence. But suppose all of them yield correct direction vectors, then to get the exact data dependence itself direction vector, we must intersect psi with the execution order dv. So, we are not yet done. The execution order dv will tell us whether there can be dependence from S1 to S2 or from S2 to S1. Okay. So, we already saw how to compute the execution order direction vector using the syntax of the constructs. So, that we do psi of V to W will be psi cross omega V to W. So, if this product produces any dot entries, then there is no dependence from SV to SW. Okay. So, this the execution order direction vector is from S1 to S2, let us say SV to SW. So, that yielded us some dot entries. So, there can be no intersection, but if all the entries are valid, we add the dependence SV delta star V to W SW to the data dependence graph. So, even now we are not yet done, we still have a star here. The actual type of dependence, whether it is delta or delta O or delta bar, will depend on the position of the references. We know that there is at least one component SV to SW, SV first and then SW is decided, but the type of delta we decide based on the position. So, if SV is on left side and SW is on the right side of the assignment, obviously it is a flow. If SV is on the right side and the SW is on the left side, then it is an anti. If both are on the left side, it is an output dependence. Now, if we got this dot and there was no dependence from SV to SW, then we need to check whether there is any dependence from SW to SV. So, how to do that? Now, we need to compute the direction vector of the dependence from W to V. So, this is where the inverse comes into picture. So, we take the inverse of the original and then multiply it with omega of W to V. Okay. So, this is the direction vector from W to V. This is the inverse of the original direction vector. So, now we are computing the dependences from SW to SV. So, if this product gives valid entries, that is no dots, then there is a dependence from SW to SV with a delta star, and again we use the position in order to determine whether it is a delta O or delta V or delta bar. So, this is how the hierarchical dependence framework is used. So, let us look at an example. Here is a nested program, I equal to 1 to 10 do, j equal to 1 to 10 do. So, there are two subscripts for this array, a I plus 1 comma j, and this side is a I comma j plus 1. Very simple reference. The first dimension uses only I, second dimension uses only j. The next example we see will combine both of them. So, the dependence equations for the two subscripts I 1 plus 1 equal to I 2 is I 1 minus I 2 equal to minus 1, j equal to j plus 1 becomes j 1 minus j 2 equal to 1. Both these must be simultaneously satisfied in order for the dependence to exist. So, GCD test with both equations returns true. So, these things we have seen before, simple equations, and hence dependence exists. So, now we need to apply the dependence framework along with Banerjee's test and determine the direction vector. So, we have equation 1 I 1 minus I 2 plus 0 j 1 plus 0 j 2 equal to minus 1. We just wrote 0 here to show that this equation, we have taken care of the j's as well, but obviously the direction vector components, the limits LBJ etc., turn out to be 0. Okay. So, we compute the values of LBI, UBI, LB with the star less than, equal to and greater than. Similarly, LBJ, UBJ etc., for star less than, equal to and greater than. For j, all of them become 0, for I they give the right values. They are all computed using the coefficients of this particular equation. The same is true for equation 2, j 1 minus j 2 equal to plus 0 I 1 plus 0 I 2 equal to 1. So, here the I components are 0 because we do not have any I index expressions in the second dimension of the array. So, here the I values are all 0, but the j values will be the ones computed from the equation. So, now, if you take LBI star plus LBJ star, so obviously LBJ star is 0, so you get only LBI star. Check whether less than or equal to B naught minus A naught, less than or equal to UBI star. So, the inequality is written here, minus 9 less than or equal to minus 1, less than or equal to 9. So, with any dependence, if there is some dependence, then this will be true. So, this is true. We try to expand the first one only, because we are now looking at equation 1 which has only I. The further expansion with we do not have to do with j, because it is all 0 coefficient in the dependence equation. Okay. All LB and UB for j are 0. So, we are not going to expand the second component for j. So, in this case again we check LBI and with less than or equal to B naught minus A naught, UBI with less than. So, the inequality will be minus 9 less than or equal to minus 1, less than or equal to minus 1, this is correct, holds. Whereas, for equal to and star, we have LBI is less than star less than or equal to, rather LBI equal to less than or equal to B naught minus A naught less than or equal to UBI equal to. So, LBI equal to plus LBI star gives us only LBI star, because the second component all values are 0. So, this inequality is not satisfied, 0 less than or equal to minus 1 less than or equal to 0. The third inequality with respect to greater than, which will obviously not be satisfied, because the first component is greater than 1 less than or equal to minus 1 less than or equal to 9. This is not satisfied. So, this is so far as the first equation goes. Now, apply for the second equation. Similarly, this is not satisfied, star comma less. So, in this only one direction vector less than comma star is correct. Okay. In this only star comma greater than is correct. The first is star because it involves I. Okay. All LB and UB for I are 0. So, no expansion on the first component is possible. So, this holds, star comma greater than holds. So, now we have two direction vectors. First one is less than comma star, second one is star comma greater than. Now, the dependence test returns less than star and star greater than, intersect these two. So, you get less than star cross star greater than equal to less than greater than, no null entries. So, recall the direction vector for the execution order dependence. So, you have S1 theta equal to less than equal to S2 etcetera etcetera etcetera. So, intersect each of these with less than greater than. So, you get less than greater than cross less than star is less than greater than, all other products give you dot value. So, they are not possible. Therefore, we get first one, this is from S1 to S2. So, we get S1 delta less than equal to S2. This did not give, if this was also not possible, let us say even this entry was dot, then we would have tested for S2 delta star S1, but now there is no need to test S2 to S1 because S1 to S2 the delta holds. Why is it delta? That is because the references, if you look at it, S1 is on the left side and S2 is on the right side. So, there is a flow dependence. That is why this particular dependence is from S1 to S2 with a delta and the direction vector is given as less than and greater than. So, this example shows that there are two subscripts, we need to reduce it to a single direction vector, check whether there is dependence, and finally, check whether the dependence is from S1 to S2 or S2 to S1. So, this is the end of this lecture, and in the next lecture we are going to look at one more example, a more complicated one, and so goodbye for today.